Hello everyone, my name is Konstantin Vladimirov and welcome back to the master's course in C++ at MIPT. This is part 2 of our lecture on modules, a continuation of our deep dive into component-based design and the modular model of translation in modern C++. Last time, we traced the path from the traditional world of headers and translation units through linkage, visibility, and the one definition rule, and finally reached first glimpse of modules themselves. Today, we'll go further. We'll explore how modules actually behave inside the language, how controlled export works, how visibility and reachability fit together, and how build systems handle this new modular reality. By the end of this lecture, you should have a full understanding of how C++ modules connect all the semantic processes we've discussed and how they finally bring real structure and consistency to the physical organization of code. And last time, we stopped right at the moment when the big questions appeared, and we didn't yet have answers. First of all, what linkage should we assign to functions and objects that belong to the module's internal implementation? External and internal linkage clearly aren't enough anymore. We seem to need something in between. Then what do we do with macro state? We tried to solve that with precompiled headers, and it turned out to be a terrible idea. If you serialize macro state, you can't merge it, which means you can only have one such header. Next, how is controlled export organized? Last time we barely dipped a toe in the water. We wrote one export function, then imported it and said, wow, it works. But come on, this is C++. There's obviously more to it. There must be rules, exceptions, and probably a few traps, and we'll see it. And of course, our lectures are all about semantic processes, so we have to see how all this interacts with name lookup, instantiation, and the rest of the compilation model. Finally, what about build systems and our beloved component-based approach? Can we keep those ideas in the modular world? That's our plan for today, to finally make sense of how modules really work. And let's start with linkage. Internal linkage has a pretty bad reputation, and for good reason. Look at this example. Inside a detail namespace, we define a static function foo. What does that actually mean? Technically, every translation unit that includes this header gets its own private copy of foo. So what's wrong with that? Well, think about dependencies. Every time this header is included, the compiler also has to pull in everything that foo depends on. All the templates it instantiates, all the types it touches, everything it includes. Those dependencies spread throughout the project like a virus. So even though the function sits quietly inside detail namespace, its definition leaks parasitic dependencies into every translation unit that sees it. That's why internal linkage often causes trouble. It duplicates code and multiple dependencies, and ideally, we'd like to stay full local and hidden, but also to exist only once, compiled as a part of the module implementation. And that means its linkage should be something different. Let's see what kind of linkage it is. And here's a piece of code that at first glance looks perfectly reasonable. But fortunately, it doesn't compile. Some overconfident programmer thought they could ban the rules of the component model and just forward declare y from the module B inside module A. Here module A, and we forward declaring y which lives in module B. And do the same the other way around to x. No imports, no dependencies, pure independence. So what do you think? Did it work? 3, 2, 1. And of course not. Of course. The forward declaration from B didn't work, and that's a good thing. The y declared inside module A is not the same y that exported from B. They just happen to have the same name, but they are completely unrelated types. And the same goes the other way around. The x inside B has nothing to do with the x exported from A. Why does this happen? Because non-exported symbols inside a module have this new linkage, what's called a module linkage. Module linkage is something like on this picture in between external and internal linkage. A symbol with module linkage is visible across all translation units that belong to the same module but completely invisible outside of it. That's a new third category of linkage introduced by the module system, and it finally gives us the control we were missing. Okay, so what do we do with macro state? Last time, we already saw how dangerous it can be. We had a header whose contents depended on whether a macro was defined, and that macro could completely change the structure or the type of function. That means that including file can affect how the component behaves at the point of inclusion. Even worse, the component itself, here, this example, can modify the macro state of the including context. So when we ask, is my def still defined after including my header h, my header.h? The only honest answer is we have no idea. Maybe it is, maybe it isn't. And that's exactly the problem. There's no reliable way to know or to isolate one's components, macro state from another's. If you did this, you probably affected this. If you included this, you probably affected this. And so on, and this is recursive. And now, when we bring precompiled headers into the picture, things get even stranger. Here what happens in our precompiled header, we define x to be like 1, and here we define x to be 2. So what's the size of the array, 7 or 8? And it turns out to be 7, because the precompiled header always comes first. No matter where you put the include, your local macro definition can't override what's baked into the PSH, but the precompiled header can override yours. That's not just weird, it's dangerous. And this is where the idea of models start to look really bold. What if we simply stop exporting the preprocessor state altogether? What if the model boundary meant a clean, macro-free interface? And the question is, what would we lose and what would we gain? Take a look at this example. We have a file, firstmodule.cppm, where we define redval as 14 and export a function foo that returns it. Perfectly fine. Then, in the client code, we do some rather creative things. First, we define foo to be bar. Then we import this module. And then, if redval is not defined, we define it to 42. And this definition definitely affects this if this were header. If this were a header, all of this would mess with the declarations inside it. But with modules, nothing happens. Macros defined outside the module have no effect on it whatsoever. the model was compiled once in isolation, and whatever macro state existed at the time is sealed inside. From the client's point of view, there's just a function called foo, and no amount of macro trickery will change that. Let me show you the codeboard. Here we are. This is module. This is some definitions. This is some definitions. And this module, as I showed on slide, is define retrieval export foo function. And we are calling this foo function here. And what do you think will be on the screen? You may now pause the video and guess. And of course, because no macro trickery affects module, the output is 14 and then 42, like you can see here. Okay. So very important consequence of this design is that the fork join point, that messy intersection of dependencies, simply disappears. In this diagram, the blue arrows represent dependency path, and you can think of them as export dependencies. Model 2 depends on Model 1 through an import. That's fine. But what if we also want Model 1 to be visible inside everything that uses Model 2, like in this source file? Of course, we may have explicit export dependency, but imagine explicit export dependency here and there and everywhere. And note, with precompiled headers, this transitive visibility happened automatically. Anything you included in precompiled header became visible everywhere it was used. But with models, this behavior is gone. So how do we make one model's export propagate through another? And this is where transitive import comes in. What does that mean? Normally, when you write import like import M1, the model just becomes available in your own compilation unit. But what if you want your clients, the users of your model, to see that same model automatically? That's what the export import does. It's both an import and an export at the same time. You import a model for yourself and immediately make it part of your own public interface. So if Model 2 writes export import M1, then anyone who imports Model 2 will also get access to everything exported by Model 1. This is called transitive import, and it became possible only because we gave up exporting macro state. And unlike include, which you can write almost anywhere, import and export import directives in modules have a strict place to live. They must appear in the preamble. A module's exporting unit, this one, starts with its preamble, which lists all imports including transitive ones. And after that comes the purview, the main body of the module that contains its exports and all other declarations. These two terms, preamble and purview, sound a bit ceremonial, but you see them everywhere, in talks, in papers, and in the standard itself. So it's worth remembering that. And this still isn't the whole picture. There's a little more to the structure of a model, and we'll get there soon. But first, remember last time we have static of different colors. Today it's export, export, export. The keyword export shows up in three completely different contexts. I would say blue, red, and purple. First, it marks the exporting unit of a module. Export module FX, except in this case. That just tells the compiler this is the module's public interface, which by the way implies there can be other kinds of module units, non-exporting ones. And what do we put here? Exactly everything that should be exported. Then we have this one. Export import AXF2. That's the transitive import form. It means that everything exported by AXF2 is now exported by AXF. And finally, export int G. That's an export declaration, a symbol made visible outside the module. Such an entity always has external linkage. It must be visible to the linker. In contrast, anything inside the module without exports gets module linkage. So just like with static before, the same keyword now carries multiple shades of meaning. But this time they are all about how a module defines and exposes its interface. So, declaration export is the most interesting for us, and declaration export have some rules. First rule of declaration export is all export declarations must appear inside the module's purview. That means they can't be placed in the preamble, only in the main body of the module. When you open an exporting module unit, you start with its preamble where imports go, and then you move into the purview where the real content lives. Inside that purview, you can have ordinary declarations like this int foo, and you can have exported ones like export int bar here. But remember, export can appear only in the purview. That's where the module actually defines what it wants to share with the outside world. And now the second rule. We already know that exports can appear only inside the purview, but there is one more important restriction. Export must never change a name's linkage. For example, if you declare something inside an anonymous namespace, it has internal linkage, and if you try to export it, you're effectively saying, make this internal thing external. That's illegal. The compiler won't let you do that. The same goes for any entity that has module linkage. Once something is introduced inside the purview without being exported, it automatically gets module linkage, and you can't later promote it by exporting the namespace or re-exporting it indirectly. So in short, you can change linkage by exporting. If something started out internal or module local, it stays this way. At first, this might feel like restrictive. Okay, this is anonymous namespace. I cannot export this name. I cannot have this name as module linkage and export it here like this one. You might want to pull in a bunch of declarations from a header like this. You see, look at this and imagine this is part of header. And you want to take a couple of declarations from header, like have them inside your module with module linkage and export like this, and this will fail. And if you try to override that, you'll run into some very interesting problems that people have in real projects. But first, rule 3. The third rule, this one confuses people a lot, including entire compilers. Export by itself does not create a namespace. Even though a module has a name, that name isn't a namespace qualifier. So when you write something like an exported variable or function, it doesn't live inside a namespace named after the module. That exported declaration is just a global symbol with external linkage. The same kind of global name you'd have in any other translation unit. The model name exists only so that you can import it. It doesn't affect how the exported entities are mangled or organized. So, if you export a variable, it simply becomes a global symbol that's visible outside the module and follows all the usual one definition rule restrictions. This is a simple global variable, nothing more, nothing less. And here's some good news. The compiler simply forbids cyclic dependencies between module interfaces. If you have one module like M1 importing another and eventually the chain loops back, that's an error. The reason is simple. Such a cycle would make the dependency graph circular and definition could start accumulating around that loop. To prevent this, the compiler analyzes the import graph, and the moment it finds a strongly connected component any cycle at all, it immediately reports an error. So unlike with errors where circular includes can lead to subtle chaos, modules make this impossible by design. And of course, names exported from different modules can still conflict. Nothing magical here. If you export a function named foo from one module, then import that module into another and try export another foo with same signature, the compiler will diagnose it as redefinition. That's because imported declarations become visible in the importing module's purview. And from the compiler's point of view, it's exactly as if both declaration appeared in the same translation unit. So when you try to define foo again, it immediately triggers a usual ODR violation. In other words, import doesn't isolate you from those rules. It simply makes all exported names visible, and any conflicting definition in the importing module will be caught right away. So what happens if both modules define a foo and you import both of them together into a third one? Undefined behavior or a diagnostic? And fortunately, it's diagnosed. And the diagnostic itself actually tells us something quite interesting. So let me click the link and show you what exactly it says. And okay, I believe this is a good boat. And let us see. So this is a main that imports foo from both modules. And in one module we do have foo, and in another module we do have foo. Okay, and now what diagnostic will be? Diagnostic is a declaration foo attached to named module cannot be attached to other modules. So it is really interesting. The name is attached. This is not like in the namespace. This is not changes the name. Global symbol is still global. Name attached like name kept in the database of this module. And name attached to one module cannot be attached to other modules. By the way, let me before we will dive deep into the attachment concept, let me show you that our favorite, our beloved overload sets are perfectly fine. Let me make this function take an int. And what if I want to spread my overload set between modules? And this is perfectly fine as well, because now when I return foo plus foo1 and I import both from one module foo without arguments and from other module foo with argument, with integer argument, and now everything is okay, and You can see 56 here. So our load resolution is successfully built. Okay, so what about attached names? The compiler says something wrong with names attachment, but what does it actually means for a name to be attached to a module? Given that modules themselves aren't namespaces, the name is not in the module namespace, it attached somehow other way. And what the standard actually says is simple. A declaration is attached to the module in whose module purview in appears. This clause from standard. There are only a few exceptions. First, if this a namespace definition with external linkage, then that namespace is attached to the global module, so you can reopen it anywhere. In one module, you do have export namespace. In other module, you do have export the same namespace. This is perfectly legal. All namespaces are attached to the global module, like non-modular part of language. And attached to global module means you may reopen namespaces module to module. And the same applies to declarations inside linkage specifications like XRC. They also attach to the global module. And of course, that's exactly why export static isn't allowed. And there's also some special handling for friend declarations, but that's a story for another day. Now, what happens if the same name is attached to different modules? And those declarations participate in overload resolution. You may, as I showed now, uh, have a complete overloading set even in the same namespace, because namespaces are attached to global module in different modules, and the compiler merges them correctly. So the overloads coexist as they should. And now, when we learned some about names, let's start with a definitive problem of smooth transition. Let's try to add some headers to module. As you can see from picture, header don't fit good enough. So look, here's our pre-module situation. We have simple function bar that uses std array. So naturally, we'd want to include array to have access to this std array. Okay. We do have import stud, but as I showed in the first lecture, import stud is really tricky. It requires quite a few gymnastics to set up. So let's now don't consider import stud. We want to include some header. And of course, ideal way is import. But if we want to include, how will we do it? Advise something to these kittens. And for transitional period, we might think, all right, let's just include array directly into the model, and that's where things start to go wrong. Now you can probably see why this is such a bad idea. Where do all those names from the header end up? Everywhere. Symbols that are attached to the global module, for example, anything declared extern C, will now start clashing unpredictably with other global definitions from unrelated modules or headers. And all other names will spoil your module linkage space. This is also a bad idea. And in other words, once you include something directly into a module, you effectively pour all of its global declarations straight into every place that imports your model. And that's a recipe of chaos. So yes, including headers directly inside a model is about the worst thing you can do. And yet, early on, people tried exactly that because, of course, everyone wanted a smooth transition. Now, what if instead of just including a header directly into the model, we try to import a header? Imagine this line sitting right there in the preamble of your model. We already know what the preamble is, so we can picture it easily. When you write include, it literally pastes the header's text into your file. But import doesn't do that. It doesn't inject the code. The names it introduces remain inside the imported unit. They are visible for lookup, but they stay where they belong. So someone came up with an idea. What if we added a preprocessor directive import that behaves like include, but doesn't textually pull in the names? It just references the existing header in modular ways. And to have something to reference, of course, this directive needs to precompile a header. And that's how importable headers were born. And that's what this import array line actually is. Here, the word import is not the same import we've been talking about all along. It's a preprocessor directive, and it works completely differently. When the compiler encounters it, it precompiles that header on the fly if it isn't already cached. Remember this whole feature? And then looks for a special file called a model map placed next to the header. That map describes which declarations are exported and which are not. And after that, the compiler injects the result into your model with internal linkage or so. And yes, this made its way into the C++ standard. Clang even managed to modularize the entire standard library, libc++, using this mechanism. But let's be honest, it's one of those simple, obvious, and wrong solutions. It looks like a smooth transition, but in reality, it's a massive, fragile hack that just happens to work well enough. All right. I promise you models, as precompiled headers do, will speed up our compilation. Let's step into our room 234, and that's where the cosmic technologies are demonstrated. And here it is, import string. Remember, I believe this is Godbolt. Remember I promised you everything will become faster, okay? We can see it becomes faster and faster and still faster. And watch closely. Here we go. Oh, compilation terminated. Exit code 143. So yes, we've definitely accelerated it. Spectacular so. What happened? Well, I'll admit, I'm cheating a little here. Godbolt always runs in a clean environment, so for it, every single compilation is a first-time compilation. It has no cache. What actually happened is this. When I wrote import string, let me show you once again, Godbolt. When I wrote import string here, Clang went ahead and precompiled the entire standard library for me. All of it. Then it cached the result in your home cache Clang module cache directory. This directory on slide. And yes, be grateful it doesn't touch your burst file. Oh, and by the way, Clang even has its own tiny language, this one, to describe header to module mappings. You can literally write a small files saying which headers belong to which module. And that how the standard library gets modularized at the first attempt several years ago. And everything is terrible here. So please, I'm asking you, don't use importable headers. Yes, unfortunately, they made it into the standard, but still don't. They are left over from the pre-standard era of modules, a fossil of early compiler experiments. And the worst part, they drag in the macro state with them. When you write import my module, that's a normal controlled import. Clean, predictable, safe. But import angle brackets my module. That's not an import at all. That's an unpredictable hole in the language. See the difference? They look almost the same, but semantically they could not be further apart. One is the modern model system we've been building toward, the other is a leftover hack that breaks it so fine we won't use importable headers. But then, how do we actually bring the include array? We still want to use stud array, right? We still don't have import stud, at least for free. And that's exactly the question that led to proper solution, proper modern solution. And proper modern solution, of course, is global fragment. We place a non-exported legacy state here at global module, and we know what global module is. It's like unmodularized part of language. But in the language, every module can carry a part of global module here. And now everything is handled in the most transparent language level way. Nothing except preprocessor directives allowed here, and you can mark your global module fragment with this module directive without name, because of course from global module we cannot export anything, so this is not export module, and global module is unnamed, so this is module without name, everything is logical. And the global fragment allows module to have a macro state visible for export unit without propagating it to others. Use this, not this. And you can keep your include array or even your define size to be 15 right where they belong without polluting the exported interface. It's the clean, language level way to deal with legacy code. We finally have a mechanism to isolate it, keep it visible where it's needed, and invisible everywhere else. And now, thanks to the global model fragment, we can finally modularize the standard library in a proper language level way. Why? Because everything inside the global fragment is attached to the global module. So when we include all those legacy headers there, like that huge beats all HPP umbrella, we are not polluting our own module with their symbols. They stay global exactly as the standard library expects them to. Then, right after that, we can open our export module stud, like this one, and simply re-export whatever we want. For instance, stud of, stud any of, stud, and so on. And this time it's perfectly valid. If we try to do the same thing without the global fragment, if we place that include inside the purview, all those imported names would gain module linkage and trigger the compile time error. But here they stay global, which makes the whole trick work beautifully. And that's exactly how modern implementations do it. You find a modern way, like in libc or libc++, they modularize the standard library precisely this way. And the little frog finally brought us the missing piece, and everything started to make sense. And now, when everything started to make sense, let's talk about names. We already seen quite a lot about linkage and exports. Now it's time to look deeper into how names actually works in modules. Here's the situation. We have a global module fragment that includes a header defining a namespace with a struct and function template foo. Then, in our exported template bar, we call foo of n colon s comma x. At first glance, everything looks fine, but what's really going on here? That's an argument-dependent lookup, right? And this expression also involves a dependent name, x. And that certain parameter x depends on the template argument, which means lookup has to happen twice. First when the template is parsed, and then again when it's instantiated. So when we actually call bar of 1, will it find foo from inside and? That's the question, and it's not as simple as it looks. You may try to pause the video now, just not make a live example of this code. Only consult standard and your opinion. And try. Is everything okay here? 3, 2, 1. Okay. Everything is wrong. But let's start with visibility. Visibility is a property of names, though interestingly it's not formally defined in standard. It's really a conceptual property. A name is visible if it can be found through name lookup. So, if we have a module A that defines a struct X but doesn't export it, and then if we import that module and try to declare a variable of type X, the compiler says no such name. That's perfectly correct. X exists, but it's not visible to name lookup. It has module linkage, and names with module linkage are not visible to code outside of module's purview. However, notice something interesting here. When we write this declaration of type Y, which itself is an alias that actually works, even though Y is just an alias for X and X itself isn't visible. And that's where reachability comes in, one of the most fundamental concepts in modern C++. While visibility is about names, whether a name can be found by lookup, reachability is about declarations themselves. A declaration can be reachable even if its name is not visible. Formally speaking, and this is a huge excerpt from the language standard. Formally speaking, a declaration D is reachable from a point P if it appears prior to P in the same translation unit, or if it appears in another translation unit that is reachable from P and is not discarded. And this is the key to the task from the previous slide. The last condition, this is not discarded, is really important. Some declarations can be discarded in the constant of instantiation, and that's exactly what we'll explore now, because it finally allows us to describe where the specialization actually live relative to their primary templates. Do you remember lecture on instantiation? We had those male deers, female deers, and like female deer must somewhere after male deer, yes? Okay, now we'll get the things crystal clear. So, what exactly is a cancelled declaration? A declaration in the global module fragment or inside a module unit is considered discarded if D is not decl-reachable. from any declaration unit in the declaration sequence of the translation unit. And please note this decl-reachable. This is another reachable. This is like subroutine for reachable. Reachability, reachable if not discarded, discarded if not decl-reachable. And the standard gives a long and very technical definition of decl-reachable. You may find it by yourself and enjoy it, but I prefer a much simple and more intuitive one that I'm actually proud of. A declaration is decl-reachable if it's used in some way that lets us tell that this particular declaration was the one being used. Okay, that's it. If the compiler can just tell, yes, this exact declaration was referenced here before any chain of instantiations, argument-dependent lookups, and so on and so forth, then it's decl-reachable. If not, it gets discarded. And let me show you an example. And this is straight from the standard itself. Here we have a module with a global fragment that includes foo.h. And inside the module, we define a template function use g. It creates an object x of type n colon x, and then calls g of t braces and x. And now inside this function, it's clear that names like n colon x, n, and even colon are decl-reachable. They are all decl-reachable. They are directly used in a way that identifies them. But n colon g is not decl-reachable here. Why? Because from this definition alone, we can't yet tell that the function g being called actually refers to n colon g. That only becomes clear later during instantiation and two-phase lookup. So in this example, g simply isn't reachable at this stage. And now let's look at this example. And this is great because it is like came from header. Here we got a function foo sitting inside namespace n and template bar that calls it. At first glance, this looks harmless, right? But think carefully. At the point of instantiation, what can we really tell? What can we really tell what foo refers to? Not at all. At that point, it could mean absolutely anything, and according to the rules of reachability, it's not decl-reachable, and thus not reachable. And because it is discarded. Formally, the name bar is reachable, but foo isn't. It doesn't belong to this translation unit, so the standard says this program should fail. Unfortunately, Clang has its own opinion on the matter, and happily compiles it anyway, as I'll show you in the link. If we will follow this link, we'll see the example where this comes from foo.hpp, and this is just like I showed on slides, and this is module, and this is inside global fragment, and this foo shall be discarded, but everything compiles just fine. Why? Because names are discarded for compiler optimization, for compiler to make BMI thinner. And now Clang has experimental mode in which Clang is standard compliant. This is thin BMI mode. I will not show it here. Please go look into Clang documentation. Okay, so this shall fail. This isn't failed practice on Clang at least. And finally, let's close the last missing piece, our specializations. Remember, we once agreed that the specialization here, this is a specialization picture, is like a female deer in our analogy. Now look at this picture. See here? No, of course you don't. She's hidden behind the bushes. Look, if you are this male deer, you don't see her. She's invisible. But do you see the road? She's still reachable. You can you can see the path leading right to her, and that's exactly how it works here. The specialization may be invisible to name lookup, but since it's reachable, the compiler can still find and use it. So when we called bar of int, there's no point trying to instantiate a new one. The existing reachable specialization will be chosen, and even though it is hidden from normal lookup. And now, let me show you how this works in practice. Just follow the link. And I believe this is another compiler explorer. This is primary template and this is specialization. And now we can formulate where specialization can live. Specialization can live everywhere if primary template is visible from this point. And here, when specialization is reachable, it is used. You see, this executor returned 2, not 1. Even though specialization is not reachable, is not visible, it is reachable, and so it is used here. Sometimes we really want to make something unreachable on purpose. Sure, we could twist the rules, hide things behind ADL or name lookup tricks, but that's ugly, fragile, and impossible to reason about. Wouldn't it be nicer to just say, you are unreachable, and send it off politely? Well, the language designers thought about that too. The feature is called private fragment, like module fragment, but private fragment. And you must remember, global fragment is always first, private fragment is always last. I think of it as a deliberate unreachability zone. At the start of a model, we can have a global fragment, at the very end, a private fragment, and everything that ends up there becomes formally unreachable. That's why the standard says a declaration is reachable only blah blah and doesn't appear within a private module fragment. And now it finally makes sense why that line was grayed out before. It referred to exactly this case. So yes, you can place your private definitions here. They'll still belong to the same translation unit, but they'll be invisible and unreachable from the outside world. There's just one little problem. Let's look how it is implemented in compilers. If you have this y variable declared here, and if you just hide this struct inside private fragment, and this struct is unreachable anymore, and try to use it here like this, then everything is okay. You have clear error. Definition here is not reachable, and it's okay. But what if we will try to hide our female deer? This is tricky part, because if we just write here module :private, okay, then you may think this will be instantiated. Instead, there will be an error. Explicit specialization declared here is not reachable. This one is not reachable. Let me show you again. This is explicit specialization must be declared before it is used. But why? Why just not instantiate it? This is left an exercise to viewers. Please write solutions to comments. Okay. And now, congratulations, you officially leveled up. We can finally describe the full structure of an export module unit. It begins here with module declaration. Then comes the global fragment, that's the zone only preprocessor directive siloed, and after the line export module name marks the start of export unit interface. Next, preamble, which holds all your imports, then the purview, where the real content lives, your declarations, definitions, exports, and so on. And finally, at the very end, you can add the private fragment introduced with module private. That's your manual unreachability zone. So now everything is in its proper place. Global fragment, preamble, purview, private fragment, the full anatomy of a modern C++ module. At the very beginning of this lecture, the part one of this lecture, we talked about the component-based approach, how each component should consist of a source file and a matching header, and how they define clear boundaries and consistent interfaces. Now that we understand modules, let's see if we can bring that same structure forward, take our old complex components and express them directly as modules. Can we keep all the advantages, clear interfaces, isolated dependencies, and still gain the benefits of the new modular system? Let's find out. Earlier we talked about how the language itself didn't really support the component-based approach. This is our huge component, but nothing in the language helped to enforce the rules, because if all these headers live in the same folder, nothing prevents us from including them directly bypass the intended structure. The language gave us no tools to protect the boundaries of a component. So now, let's take this same example and move toward a proper modular component model. And we'll do it in 2 steps. Step 1 is splitting the module into multiple translation units. A single module can actually span several files, but only one of them is the interface unit, the one that declares what gets exported. All the others are implementation units providing the actual definitions. This is very convenient. It lets us move the heavy internal parts and even any messy dependencies out of the interface and into separate implementation files. So, one export unit, any number of implementation units. The interface describes what's visible. The implementation unit defines how it works, and everything declared in the interface remains reachable from the implementation side, but not the other way around. And now there's another interesting case. Suppose we have a top-level Model C that re-exports to others, A and B, and that's easy to do. We just use transitive import. But sometimes we don't want A and B to exist as standalone modules. We don't want users importing them directly. They're just internal building blocks. Still, we'd like them to have clean internal interfaces so that C can use them in a modular way. So how do we make a module that's part of another module, visible to its parent, but invisible to everyone else? And that's exactly what partitions are for. A partition is like a submodule, a self-contained piece of the same module. And in build systems, submodules are the root of evil. But in modules, submodules like module partitions are great. Each partition has its own translation unit, just like a normal module. This is a separate file and this is a separate file, but it shares the parent's module name and internal state. So in Model C, we start with an interface unit that exports and imports, like imports transitively, all its partitions. And that's the rule. You must explicitly list them in the preamble. Then each partition becomes a little exportable unit of its own, but still belongs entirely to Model C. In other words, we are now building our model out of smaller modular blocks. A proper modular composition is not just pile of headers. So, here what's really going on with partitions. Each partition is its own little export unit inside a larger model. And then they can import each other, but only through the parent's module's namespace. They all live under the same roof. And here comes the fun part. See that single colon in the model, component colon general? That's completely new use of the colon in C++. Until now, the language had abused plenty of operator, but the single colon had stayed relatively innocent. Now it finally has a new distinct syntactic meaning. It marks a partition of a module. So when you read module component colon internals, think of it as saying this is the internal partition of module component. Each partition has its own interface, and together they form a cleanly layered component. And this is where partitions start to shine. This is another example from C++ standard, rather convoluted one. They let us truly split our interfaces and implementation. Look at this rather strange, but rather impressive, I would say, setup. We have one top-level module A. A exports a partition foo. Then that partition itself imports another partition, which is internals. And notice, we can also import partitions not just from interface unit, but from ordinary implementation unit as well. This means you can structure your model however you like. Clean interface partitions at the top and share it like this module A internals partition, and for module A implementation unit import internals another time. You see? Here, without that import internals, the function bar simply couldn't be defined. Its declaration would be unreachable. But once you import the internal partition, everything fits together. So yes, you can have partitions that export things and others that don't. They're still part of the same model, just playing different roles: interface partitions, internal partitions, implementation partitions, whatever makes your components easier to organize. And remember this inversion of dependency slide last time? When I said you'd have to flip your mental model, that's exactly what I meant. Think of a model as something that produces not a single thing. The model is like a heap of partitions, components, implementation units. Here is a lot of things, but only two well-defined outputs. A BMI file, that's the compiled interface, and the object file, that's the actual compiled code. The BMI plays the same role that a precompiled header used to. But now it's a proper language level construct, and this idea scales. Even if your component module spans many files, in the end you still end up with same two products: the BMI for the compiler and the object files libraries for the linker. So now let's finally talk about what this mysterious BMI actually is. The funny thing about BMI is that everyone agrees on the concept outlined here, but absolutely no one agrees on the format. Clang calls them PCM files. GCC is GCM files. MSVC prefers IFC files. And all of this not just different names for the same kind of weird artifacts. Um, this is different artifacts, different files. Each of them stores the compiled representation of a module's interface or header unit. But the structure of that file is completely compiler dependent. It might contain serialized TST nodes, compiler-specific metadata, bits of machine code, whatever intermediate representation the implementer decided to use. And of course, if you try to fit a GCC-produced model into Clang, no, it won't just work. They don't speak the same dialect. Not yet, anyway. Right. So, here, we don't give the answer yet, just raise the issue. Let's think about it. If every compiler stores its modules, at least export parts of its modules, in its own private binary format, then what does distribution ever mean? We can't we can just publish a single binary module and expect it to work everywhere. The format isn't standardized, and it even encodes compiler options, target triples, and so on and so forth. So when you say, I want to distribute a C++ module, what are you really shipping? A BMI, a set of object files, and so on? And how do you make sure users can actually import it with their toolchains? Okay. Basically, realistically, we have two options. One for Fox and one for Frog. First, distribute the export unit together with a precompiled library. Basically, give a people your library, static or dynamic, and along with it, a BMI source that describes the exported interface. And second, distribute full source code of the model itself. So everyone builds their own BMI locally, uses their own compiler. Both sound okay until you hit the real issue. What if your module depends on other modules? How will a build system know that? How will CMake or Ninja, whatever you use, figure out that your module needs to be compiled after some other one, and that it needs to import its BMI before building yours? That's the heart of the problem, and it's not actually new. We've had the same headache for years with include dependencies, only now it's a lot more explicit. Alright, let's go back to the good old world of Make. Here's a tiny fragment of a Make file, a real classic. You could chunk it, a few sources, a few object files. Looks familiar, right? Now, before I go on, put the video on pause for a second and think, what's wrong with this Make file judging on this snippet? Seriously, take them out. If you've ever written Make files by hand, you should be able to spot a few problems right away. Ready? Ready? 3, 2, 1. Okay, let's talk about it. And this already looks a lot more serious, doesn't it? Now we are finally collecting dependencies, but what does that ever mean, collecting dependencies? How are we actually doing it here? Take a closer look at this slide. What is all that supposed to be? MT, the strange mix of double signs and calls. What's going on here? And if you've never dealt with this before, it's the compiler quietly building a map of which source file depends on which targets or which headers. And this is how Make learns when it actually needs to rebuild something. And yes, those cryptic flags are the key. We'll talk about what they really do, especially that mysterious MT, in just a minute. And here lies the secret behind why the old system worked so well. Includes participate in lexical analysis. They are handled entirely by the preprocessor long before the compiler even starts building an abstract syntax tree. That's why we can simply run a command like this and instantly -e means only run preprocessor and instantly get a neat makefile rule listing every header our file depends on. This trick works because include is just textual substitution. The preprocessor sees everything, every header, every include shape, and can describe it in purely textual way. That's exactly why Make and CMake handle include so easily, and why every compiler supports this mechanism in one form or another. But modules are a different story. They aren't part of lexical analysis. Models live at the syntactic level, and that changes everything. Here, where this thing suddenly gets serious. Do you really want to perform full syntactic and even semantic analysis of C++? A language that, as well as we'll soon see, is basically Turing completed a compilation time, just to figure out which models depend on which. Of course not. That's exactly why the language designers introduced all those strict rules. Imports only preamble, single export unit, well-defined stages of module structure and compilation. All of these exist so that compilers can get away with doing a limited, lightweight form of syntax analysis. That lightweight analysis stage is called collate. Look, tools like what occurs, Clunks, Come Depths, or their GCC and MSVC counterparts use it to collect module dependencies safely and predictably. And this is where this document P1689 comes in. It defines a unified format for this dependency information. If you've ever wondered why module CMake suddenly started working with C++ modules, this is why. Without this document, without P1689, each compiler would have produced its own incompatible dependency data. Now at least they all speak the same language, a simple JSON-based format supported across Clang, GCC, and MSVC. So build tools can finally make sense of module dependencies. And here's what that format actually looks like. It's nothing mysterious, just a structured JSON file described who provides and who requires which modules. Each rule corresponds to one translation unit. It records its primary output, the module it provides, and all the other modules it depends on. This tiny fragment already shows how a build system can reconstruct the full dependency graph, who defines what, who was what, and which file each module lives. This is not human-friendly, but it's incredibly useful, the first real bridge between compilers and build tools in the modular C++ world. Right, so a few more details about this file set 66 module about CMake support. Because after collate is done, now CMake can support mod. Each target sources in CMake after CMake 3.28, every target sources call can now declare a file set, basically a logical group of source files that serve a specific purpose. For modules, that purpose is clearly defined. All files listed under file set are treated as module interface units. CMake then takes care of several things automatically. It scouts each interface unit for its export module declaration to determine the module's logical name. It generates the correct build order by consulting the P1689 dependency information. So modules that are imported are built before the ones that depend on them. and it ensures that those CPPM files are compiled with modular flags and that the produced BMI artifacts are passed correctly to dependent targets. We can have multiple file sets, for example, one for public modules and another for private implementation partitions, but all of them follow the same idea. CMake treats them through explicit declarations rather than fragile includes cake. This is still evolving, but it's already enough to build real modular projects reliably. Again, I'll have a good talk on this in the bibliography for anyone who wants to experiment with it hands-on, but let me show you an example. And here's Godbolt. Add C. This is minimal required CMake. This is project definition and C++ language. And this is executable. And executable here, let me do it this way. Yeah. And executable here imports one module, and this module fxmcppm imports another module, and another module had both export unit and implementation unit, and implements some logic, I believe 242. And then this is CMake list. We have those CPP files and implementations unit as simple files, and interface unit in modules file set. And this is important. You need to add standard as a target compile feature. And now, if you will see here at executor, you'll see that full build have 10 stages. We are scanning everything for dependencies. Then we generated dynamic dependency file, this JSON, and then we are building all dependencies in proper dependency order. And you can see linearized direct acyclic graph here in steps 6, 7, 8, and 9. And finally, we are linking final execute. Okay, so some homework. It is a real project, a course project, I will call it. And it was 20 points, but those points may be distributed between the team members. You'll be working on a model-based implementation of special language that is designed to be hard to parse. And at minimum, you need to implement a simple interpreter, but if you want an extra change, try to meet LDMIO. It will make a design much closer to a real compiler. The deadline for this assignment is 2 months from now, and you're allowed to work in teams up to 4 people, can carefully divide responsibilities, and remember clean model structure will make life much easier once you start testing. If you are not on this course and you're just watching it on YouTube, you may share your solution in the comments here on YouTube, and you may review solutions of each other, and it's a lot of fun. Please do it to make some hands-on experience with noodles, flags, dissolve. Flags and dissolve generate some headers. You will want to code those headers in global model fragments. Everything I told in these lectures will help you, I believe. Okay, and finally, let's go over the reviews for today. And the material here is fairly recent because C++ modules had only just reached a stable state across compilers and build tools. And let's start with Daniel Langer, the 3 secret spices of C++ modules. This talk was among the first serious attempts to explain visibility, reachability, and name lookup in the new modular world. It may feel a bit surface level in places, but it's absolutely worth watching. Just increase the playback speed a little. Next, Andres Weiss, C++ modules getting started today from 2023, despite the humble title, it's sorted and lively introduction. I'd say one of the best first encounters with practical models. And then Luis Carcampos, a review of the current state of C++ models. Luis is one of the maintainers of Kona and part of standardization efforts for package management in C++, so his perspective is especially interesting. how to distribute and package modular libraries across ecosystems. Very insightful and also a bit of a preview of the future. And here Bill Hoffman imports CMake, and this is almost a victory lap. After several years of we are still working on these talks, this was the moment when CMake full module support finally landed, and Hoffman walks through the real implementations and show how file set and P6989 data fit together. A must watch if you want to use modules seriously in your builds. And then a few talks in Russian, optional but highly recommended. And this is Anton Pavlyuchin's practical adoptions of models. Excellent, especially his discussion of modularizing most libraries to different approaches, to different outcomes, were worth studying. And finally, my own models in C++ problems and solutions on C++ Russia 2025, a deeper dive into the semantics and structural issues we discussed in the course. And with that, we close the main part of our journey through the semantic processes of C++ models with the last missing piece, connecting linkage, visibility, reachability, and name lookup into a coherent mode. Next time, we'll climb even higher to the world of compile-time computation. We'll revisit rotary learning, but from the perspective of metaprogramming, talk about sphere, context evaluation, and the deeper theory behind how C++ reasons about code that runs at compile time. And that's going to be the start of our graduate level exploration of metaprogramming, place where templates, deduction, and reflection all meet. But it will be in the next lectures, and that's all for today. Thank you, Error.